Okay, so of the two types of SPM, we're gonna first cover AFM, atomic force microscopy. Sometimes it's just nice to kind of see a picture of what these instruments look like. This is very small. It's very relatively expensive. You actually can build your own, it turns out. In the old days, this is what people did. But this is a relatively small instrument, okay? And so you're gonna put in like a solid surface, some sort of sample. Could be a piece of glass or maybe a piece of glass with a metal deposited on top of it, whatever it is, right? But it's gonna be a solid in most cases. You can do liquids in a solid, like in a solid container. But most of the time, you're just gonna be talking about solids here. And what you're doing is you have some sort of very precise tip, very sharp, okay, tip. When I mean sharp tip, it's almost atomically precise, okay? And I'll talk a little bit later about how you might make these tips, okay? You buy them nowadays a lot of times, but you can make them. And what you're going to do is you're going to be moving this tip around on the surface. And what you're going to be, and basically the information, you're going to get information about the topography. You're making a map, okay, about the height of the sample, okay, as a function of the position of the tip. You're making, it's a topographic map you're making, okay, but it's not a hiking map now. It's a map of a tiny surface at like a molecular level, which is pretty awesome. So you use something called a piezoelectric crystal, which basically allows you to have very precise control of the position of the tip, okay? Talk about that in a second. But what you're gonna do is you're gonna shine a laser and the back of the tip is gonna be reflective. And then you're going to use a photodiode to determine the position of that laser, right? And what's gonna happen is this tip is gonna bend. It's called a cantilever. This cantilever is gonna bend, okay? And the tip, so if the tip hits something, it's gonna bend. And that's gonna cause this angle that the laser shines at to change, right? And that's gonna cause the position of the laser light that's detected by the photodiode to change. And so from that, you can back out how much of the tip bent. And based on how much the tip bent, we can back out how tall the sample is. That's the idea. So you know, probe contacts are these tips. They're contacting the specimen physically, and it's moving up and down just due to repulsion. It's like you're trying to jam a stick into the ground. It's going to want to bend, right? So there's physical repulsion just due to van der Waals forces. Okay, it's van der Waals forces on a microscopic level. Okay, on a macroscopic level, we say it's Newton's second law or something, right? So these are all examples of cantilevers, right? You know, suspension bridge. They're just things that are overhanging, and this will bend, okay, if you apply pressure to it. That is the idea here. So the AFM uses piezoelectrics. These are crystals that acquire a charge when they're compressed, twisted, or distorted. And they are what allows you to produce the nanometer level motions, okay, in the X and Y, that then allows you to read out the Z motions. And so you can basically apply a charge to these crystals and then cause them to change shape. So you can control the voltage or how much charge you apply to these crystals, and then very precisely at a molecular kind of level precision, you can change the position of these crystals, basically, okay? And so that allows you to control X, Y, very specifically dimensions of your tip, and scan it around your surface. You're basically going to scan this tip around your surface and then read out through the deflection of the laser beam of the cantilever the height, the Z position, okay? And so just so you know, the most common piezoelectric is a ceramic material. It's a lead zirconate titanate. So it looks kind of like this. And so AFM probes are very, very small. They must be very, very small if you want to get really high resolution. If you have a big tip, you know, that's not very sharp, dull tip, you're not going to have good resolution. You can make these things, the tips, out of many different materials: gold, silicon nitride, quartz, many other things. Sometimes they'll have different hardnesses, okay, which can be useful if you're probing like hard or soft materials, right? And so, right, you have this deflection, and it's the laser beam bouncing off of this deflected cantilever detected by the photodiode that gives you the height information. So you can get all sorts of AFM images. If you just Google image AFM images, you'll come up with all sorts of cool things. Here are some chromosomes, and you're getting, you know, nanometer, micron scale resolution is easy. Nanometer level resolution is a little bit harder, but you can get it. And you're looking at you can look at non-conductive or conductive materials with AFM. It just relies on contact. You can also get, not only can you get topography information, when most of you are talking about that, but you also can get mechanical properties, because you can now actually, if you have a really hard chip, for example, you can like poke through stuff and then retract out of it. And so you can get what's called the Young's modulus, for example. That's one thing you can get out of this, which is a measure of how stiff a material is. So you can see I showed you some Young's modulus here for various different materials. Now just going on a little bit of a tangent on Young's modulus, but AFM can allow you to measure the nanoscopic mechanical properties of materials. That's why this is so cool, because sometimes the macroscopic mechanical properties can be different than the nanoscopic mechanical properties. I mean, think about like a covalent or ionic bond, extremely, extremely strong, right? Or in extreme case, think about the forces that hold protons together, the strong force, right? Extremely, extremely strong. You need a nuclear reaction in order to break those forces up. But, you know, if you look at a piece of paper, you can use your hands to rip it. So obviously, you know, the stiffness of the atoms, the nuclei inside the atoms of paper are very different than the stiffness of bulk paper, right? Like as a whole. And so that's what I'm trying to say. This is cool because we can now probe using AFM the nanoscale mechanical properties of the material and maybe compare it to the macroscopic. And so you can see, you know, measured by AFM, carbon nanotubes here have an insanely high Young's modulus. In fact, the highest Young's modulus known at a nanoscale level. And so people are very excited about this. You can get really, really, really strong materials, carbon nanotubes. You know, they're used in making like tennis rackets and alloying certain materials, right? Composite materials. That's a cool application. A cooler application that people are talking about is like, can you make a space elevator? And it turns out if you have this sort of order of Young's modulus, really, really strong material, you can. What is a space elevator? It is something that allows you to not have rockets, okay? It would just be a really, really long, big tower that could take you out into low gravity orbit. And so now you can transport things into outer space without having a rocket ship. Save a lot of energy, save a lot of time, save a lot of money. How do you build that thing? It has to be super, super strong, right? So that it can do this. So people are thinking about using carbon nanotubes. The problem is carbon nanotubes are so small, you can't build a tower out of them. And you can't figure out a good way to link a bunch of small nanotubes together. That would be one option, link a bunch of small nanotubes together. Or you're going to have to build a really, really long contiguous nanotube. Both of those things are super, super hard. All right, in the next video, we're going to talk about the second type of scanning probe microscope, the scanning tunneling microscope.